And so Operation Every Little Thing Gets Done continues. I am uploading to YouTube as we speak something that I really never thought was going to be a reality on iPhone. There it is occurring. How old is iPhone? It came out somewhere around 2007, and so it's 2022. So 2017 made 10 years. 18, 19, 20, 21, 22. 25 years. Oh, it only took 25 years for the iPhone to get doing what the Amiga computer could do in 1985. So, you know, things today are really catching up to the era of Back to the Future. The irony is, Back to the Future was the future, and then we regressed into the past for a good long while. And things are catching up here and there. Now, the fact that it's mobile and fits in your pocket, give credit where it's due, that's just cool. But the level of multitasking that, you know, the Amiga portrayed, was able to do, is only just now being caught up with other things. Although, you know, the amount of bits and bytes that are being pushed around is quite amazing, right? The Amiga probably could have never handled that much data, but you know, what it was today projected forward, you know, keeping pace with advancements in technology, would have been unrecognizable as from Earth at this point, right? So if it was 30 years ahead of its time 30 years ago, it's probably pushing 35 years ago now. 85, 2022. It would have been unrecognizable as technology from Earth. You know, people say, yeah, should I ramble? Should I really go on wacky tangents? So, I've talked so much about personal and professional lately. I might as well move along to the speculative and the fantasy stuff that I love so much. So I'm a sci-fi guy, but I'm a sci-fi guy greatly because I'm a science fan too. I'm subscribed to popular science up until the internet, or the web, I should say. And that was my internet fix before the internet, because popular science was really cool that way. I work for the company that publishes PC Mag and IGN and Mashable, right? So, you know, I align to my vibe for sure. But back in those days, it was popular science was my really big science thing. And and we had anti-gravity in the 1950s. The moment, you know, quantum mechanics was figured out, and the Casimir effect and the Lorentz force, we knew it was possible. We knew anti-gravity was possible. You know, call it anti-gravity, but, you know, it's, you know, non-combustion propulsion systems. We knew how to do it. Now, other things from that era that we knew how to do included the atomic bomb, atomic energy. But the difference is, if you use it to decisively end a war, you can't hide the bang. You can't hide the bang of using an atomic bomb. So the atomic bomb moved from the realm of closely guarded secret to well-known. Now, say you had some sort of thing like that had no boom. Didn't have to make a boom. It never had to make a boom. In fact, its nature is more of a quiet, stealthy thing, and its whole advantage comes from the quiet stealthiness, as opposed to the explosion. This subtle technological tool. Now, of course, there's patents on this that, you know, the Navy says this is real. There are operational models of this thing. And then the naysayers are like, well, that's to throw off China. And people like me are like, yeah, and it's, you know, the 1950s, 60s, 70s, 80s, 90s, 2000s. It's 50 years, you know, after the fact. It's 50 years late. So instead of like surprise and, you know, it's a trick to throw off China, I'm like, well, you know, at least they got to talk about it a little bit. They can't. I say they can't as if it were anyone but us. Now, we can't. You know, some other countries might have it. The United States certainly does. We are amongst the countries with anti-gravity technology. And I'm not like a wacko fringe person on this stuff, you know? This is mainstream. The government is saying, yes, there are UFOs. We call them UAPs now. There's things in the airspace. We don't know what they are. And, you know, again, the naysayers are like, oh, well, that's just to throw off enemies and stuff. It's just more of, you know, the SR-71 Blackbird and, you know, the stealth bomber type stuff, because you got to throw off the enemy. You got to work on stuff and you got to throw off the enemy. If you work on it, throw off the enemy. And, you know, throw them off your scent to get them to spend lots of money on the wrong projects. Okay, it might be that. But much more likely is that, you know, we figured out how to tap these forces. Things like 0 point energy. Not for free energy, mind you. There's still no such thing as free energy. So it hasn't been common. The cat hasn't been out of the bag, such as it were, because you needed two things to make anti-gravity practical. You needed a nearly unlimited energy source. You needed something like fusion reactor. A small nuclear reactor boots the process, and then a electromagnetic resonance chamber amplifies it up, and then eventually fusion starts happening in that chamber. You know, that's where the cylinder-like shapes come from, or the tic-tac-like shapes, because that's the general shape of, you know, EM waves going back and forth in a resonance chamber. You ramp that up enough, and the quantum foam, the rippling stuff of the fabric of the universe, gets magnetized in an absolute position. We live in a relativity and stuff, but honestly, it seems that if you create a region of magnetized space, and then you bring a superconductor into that region, it locks in place. It hangs there, okay? So you need the power. You need to ramp up the power to polarize the, you know, quantum foam. So it's a power limitation, which we're surpassing, which we're, you know, some of the various fusion technologies get us to that point now. But then the second thing you need is computers for navigation, because who's to say that with the Earth rotating and the Earth rotating around the sun and the sun rotating in the arm of a galaxy, that if you magnetize a polar region and you put a superconductor in it that holds steady to that spot, it's not going to shoot off because that region of space is actually moving. We don't know. It might be that everything's expanding at such an equal space or rate, and, you know, just like the raisin cake, the rising raisin cake model of the universe, such that there's something like absolute positions, in which case the computer guidance wouldn't have to compensate for a wacky spiraling, but it would still have to do quite a bit of work to create stabilization, similar to the helicopter problem with a tail rotor. And so, of course, things like, you know, machine learning and just generally, you know, more powerful computers certainly helps with that problem. So the energy piece coming into place and the computer navigation piece coming into place. If we understood how to do anti-gravity in the 50s, this is when it's crossing over in the technological readiness scale from things like, you know, TR3 to TR4, some of these uncanny voids where things really fail to leave the lab and to get into everyday use, TR6 to TR7. And, you know, TR10 is part of our everyday lives. They had to add things to the technological readiness scale to get it on a scale to 1 to 10. But from, oh, this should be possible, like, you know, with Casimir and the Lorentz forces in the 50s and quantum mechanics, to, oh, we got something working in the lab, like proving it, the success assured moment of like the Wright brothers and Kitty Hawk with the wind tunnels. That's like TR3 to TR4. Working prototypes, you know, getting it out of the prototype controlled conditions into the real world. That's, I believe, like, you know, TR4 to TR5. And, you know, when the rubber hits the road, so you're working on a rubber for a tire and it hits the actual road, TR6. And in actual production and, you know, early models and stuff, TR7 and so on, through technological readiness. So anti-gravity devices of various sorts have probably been going through these stages in the labs under various, you know, different efforts with various different names we've heard over the years by various different countries and companies. And yeah, so this is one of the wacky ones. I wonder if I'll actually even post this. So I guess since I'm still continuing on, I got that shelf packed up. It's the main thing I want to do. I got one more piece here. Okay, I'm going to do this last piece, and then I'll be on with my night. So I talked about the quantum phase locking approach to anti-gravity. It's really nothing different than you can see on YouTube if you Google quantum phase locking. It's just the part that plays the role of the magnet, of the natural magnet. You know, oftentimes a neodymium magnet, neodymium, which is really an alloy. It's not pure neodymium. It's you know, steel and other things mixed together with some portion of that and then coated with some sort of coating to make it all that, you know, silvery metal look. It is a metal, but it's not nearly as shiny. It's more like a ceramic under there. But the role of that natural magnet is played by a electromagnet that is created through, you know, polarization of space-time, and then locking a super conductor in it, because superconductors, especially the layered kinds, you know, yttrium, barium, whatever, copper, they have these layers, and then the magnetic field somehow gets trapped in those layers, and it keeps it, through the very imperfections of it, locks it into place. And then, you know, you make that into like a train rail through the air, through space, underwater. These things can go underwater just as well as they could in space. But this is just one of the approaches to anti-gravity, one of the particularly less stellar ones. It's not great for interstellar travel, you know. On the other extreme, there's warp fields, right, which are looking more realistic, again, detected at the level of the Casimir force. During Casimir force experiments, we detected, you know, possible warp fields. That's at the other extreme, bending space-time for faster than light travel. Still might not be, you know, in our future. You know, it might not be realistic. The other one of quantum phase locking is more than realistic. It's actually in use if you don't count the polarizing quantum foam part of it. But the other types, if you use normal superconductors and magnets, it exists, it's there. And in between are other things that are also quite fascinating, which have to do with gravity lensing, just bending gravity, gravity fields, gravity emitter, gravity field emitters. Again, you'll see it in the Pius, Dr. Caesar Pius patents, the US Navy patents, where they claim, yeah, this stuff is real. They cover some of the more basic anti-gravity, but then they also talk about gravity field projectors that work starting out the same way with the resonance chamber of the electromagnetic energy, but then they have counter-rotating, I'm not exactly sure, it's counter-rotating pieces in there that moving through that field emits waves of gravity. And that emitting waves of gravity can create what's in the Bobiverse sci-fi series called a surge engine, because you fall, you can literally be falling towards where you want to go. I want to fall in that direction. I fall in that direction. Again, not the most stellar anti-gravity. It's not great for interstellar travel, but it's certainly good for getting you around the local solar system and deflecting asteroids and various other fun, force field tricks. Distinctly different from quantum phase locking, right? So also fairly realistic. It's been proven over the past few years that gravity lensing occurs. The gravity of planets is bending the light coming around from stars behind them, and we are seeing that lensing effect that Einstein predicted. So with the power of a star or a planet, you can, bend gravity. Of course, space-time bends, but, in ways that are more practical, perhaps. But then again, you got the energy problem, and more of an energy problem. Quantum phase locking, polarizing the quantum foam probably doesn't take that much power, but bending gravity enough to have a local, distorted gravity field to move you, probably a bit more energy. So anyway, there's that. And I don't necessarily think, aliens are visiting us. There's probably life somewhere, but we're probably amongst the first. The universe is only, 14.5 billion years old. The Earth is 4 billion years old. Everything's young. We're young. Universe is young. Earth is young. Life in the universe is young. We're amongst the first. We shouldn't be that surprised. We are the aliens. We're the ones who are either going to be a problem or not a problem to things out there. We might be getting visited, we might not be getting visited, but it's almost besides the point. The question is what we are going to do as we crack these final, pieces of the puzzle to either start the galactic community or to join it, one way or the other, right? Anyway, that's a fun place to end. Thanks for joining me on this rather wacky video. Hope to talk to you again soon, and don't forget to subscribe.